by equating the chemical potential of the vapor and the liquid by using the departure functions, we arrive at the following equation, which if we take a given a temperature T1, right, which actually lies between the critical point and the critical temperature. Let's leave out those temperatures. In that range, we are tracing the coexistence curve. We're given a temperature, we want to find the saturation pressure corresponding to P1, which will be known as P1 sat. Right? So then we will also denote the saturated liquid and vapor volumes corresponding to their all functions of temperature. This is VL of P1 and this is P. That is the saturated vapor volume corresponding to the temperature T1. The liquid and vapor are in coexistence, right, at the same temperature and pressure. So the governing equation is given as this, and so it has an interesting geometrical interpretation which leads to it deriving the name as Maxwell, attributed to Maxwell, probably got this first. It's also referred to as an equal area rule. Equal area rule means, let us consider that this is the saturation pressure, which intersects the equation of state like this. This is P versus P diagram at T equal to T1. All this you have to keep in mind. We're talking about a particular temperature T1. Let us say the P equal to P1 sat cuts the isotherm like this, and what this condition means geometrically is that this area is equal to in magnitude to that area. So we may also write this as A1 minus A2 equal to 0. Another way of looking at it, which will actually help us to scale the pressure, as I said, this has to be done iteratively, because at the outset, I know neither the saturation pressure nor the liquid and vapor volume. So this equation has to be solved along with the equation of state. Right? Along with the equation of state, it has to be solved. Right? So that's how I find the volume. So along with this, you have to solve to get the saturation pressure as well as the liquid and vapor volumes. So this was an iterative procedure. We came to a stage where we have to change the pressure. We take an initial pressure that lies between PA and PB. If it doesn't satisfy the liquid, then we need to have a way to update the pressure in the iterative process. Right? So for that, it's useful to look at this. Because we also saw, depending on whether A1 minus A2, that is this, I may call this, suppose let us say, I start with a value P0, that's the initial guess. So I'll call this PA, and this will be PB. So I'll start with an initial guess, which lies between PA and PB. So now I will go, once I have chosen P0, I will determine an initial liquid volume and an initial vapor volume corresponding to the equation of state at this temperature T1. So I will solve the equation of state. Right? So the equation of state has three variables, P, B and D. So P will be P0, D is T1, that's given. So I can solve for it, I will get a cubic. If I choose the pressure between PA and PB. As we have already seen, the middle root has to be discarded. The lowest root becomes VL0 and the highest root becomes VB0. Right? So I will now calculate the quantity M0, which is defined as P0 times V1 P0 minus V1 L0 calculated, then we saw that if m naught is actually greater than 0, right, then p1 has to be less than p naught, and if m naught is less than 0, m naught is actually this area minus this area. This area is greater, that means we have chosen a higher pressure than what is required. We have to bring down the pressure. And if m naught is less than 0, that means P of 1 must be greater than P of naught, what I have chosen. This will be now the new pressure with which I have again calculated new m, which you can call it m1, for instance. Right? So we saw that one way of doing it, P of 1 is equal to P naught, then minus delta P is greater than 0. And here to increase it, I'll simply add a constant. This might be okay. We can do it with some books also. Give an additional way which could probably be faster, but you have to always guard whenever you update the pressure, whatever means you use, you have to also make sure that it lies between PA and PB, right? And so let's look at that criteria that's, for instance, given in YBC law. So one way of writing mu minus mu Ig at any temperature and pressure, and if you look at the definition of the fugacity, it can be written as RT log F over P. We define the fugacity in terms of P times exponential mu minus mu Ig by RT, right? But I can invert that and get this expression. So what we have essentially done in this whole process is that we have subtracted at some P1 and the corresponding P1 sat, right? P1 is actually P1 sat here. Right? So we subtract the two. That is how we got this. So this left hand side is really mu B minus mu Ig minus mu L minus mu Ig. And that has to be equal to 0 at the saturation pressure. Right? So I can also rewrite this difference, this quantity m, which has to vanish, as RT logarithm of Fp by Fl. Now what some of these algorithms do is they scale the pressure according to the ratio of the fugacities, right? So because the pressure has the same unit as the fugacity, so that is probably used. And for instance, now we can translate the fact that if m naught is greater than 0, then what does it imply? It implies that Fp naught by Fl naught is actually greater than 1. Right? Because this is greater than 0. So the sign of this whole thing, RT logarithm, is actually equal to m, right? Actually comes from logarithm of Fp by Fl. If this is to be greater than 0, then this ratio has to be greater than 1. If it is less than 0, less than 1. So we could think of another way by which we put P of 1 as P of naught times, rather than just adding a delta P, whatever may be the difference between P naught and P1. We could scale it in terms of the ratio of the fugacity. So I am correlating this because the initial one is based on m greater than 0 and less than 0. Now I am translating it as Fp naught by Fl naught greater than 1 and less than 1. So it is just going to become like that. So this can be written as, so now how do we want this to be? This can probably be written as Fl of naught. So we can see whether it accomplishes what we want. So if clearly from this, either it's Fl naught by Fp naught or Fp naught by Fl naught. Let us see whether what I have written is correct or not. If it is Fl naught by Fp naught, then if Fl naught is greater than Fp naught, right, then P of 1 would be less than P naught. I'm sorry, if Fi naught is greater than Fp naught, then P of 1 would be greater than P naught. Is that what we want? That's exactly what I want. If Fi naught is greater than Fp naught, then Fp naught by Fi naught is less than 1, then that corresponds to the case where M naught is less than 0, right? So, which would mean that P of 1 has to be greater than P naught. So, I'm just putting this in terms of the ratio of the fugacity of the vapor and liquid, or liquid and vapor. If you want to write it in terms of M, now what you can see here is that the way you look at most of the textbooks, look at this, they'll actually write only the expression for this, which is actually RT log by P, and this is actually RT. And then they will say, go and calculate the Fp and Fl, right? And then for a chosen pressure, and see if Fp by Fl is greater than 1 or less than 1, which one is greater, and then use this criterion. But what we have done, I think that is numerically unnecessary. We having to compute more terms. If you see the expression for the departure function, it has one integral plus a whole bunch of other terms, and we sort of combined everything, cancelled the unnecessary terms, the terms that are equal, and arrived at the simple expression, which is much more revealing, right, and simpler, easier in fact to remember than the departure functions themselves. This also has a very good geometrical interpretation which follows directly from this equation. Otherwise, it's a bit contrived way you have to give the equal area rules proof geometrically, right? So I don't see any reason to calculate the fugacities individually. In fact, fugacity is, I think, an overrated quantity. All I need to calculate is M naught and then M1 and so on, right? But however, this idea is useful stated in terms of fugacity, right? Because you see that the fugacity pressure scale as the ratio of the fugacities, right? Pressure for the next iteration, the ratio of that to that, and that makes sense because pressure is sort of has the same units as fugacity, and you can use this as a good way to scale the pressure. So if I want to write this whole algorithm in terms of M, which is what we are going to calculate, I can simply write this as, I'll just copy it. We'll get P of 1 then is equal to P naught times exponential of minus M naught by RT. If I were to write this, if I written this first, without explaining to you how the fugacity comes in, you would have wondered why choose an exponential of minus. This would accomplish the same thing. If M naught is less than 0, you can easily verify that P of 1 is greater than P naught. Right? If M naught is greater than 0, you can easily verify if what I have written is correct. This is what I have here. Right? So this will satisfy, accomplish that. But you might wonder why choose exponential of minus M naught by RT. Actually, the reasoning comes from this, which is easier to comprehend, to look at the pressures in terms of the ratios of the fugacity, and then translate it in terms of the quantity M naught. So what I would say now, I'll complete the algorithm, right? So the algorithm would be that first choose PA, choose P naught, calculate M naught, right? Then P1 is chosen like this, and then simply proceed, right? So we can have a general expression that P of J plus 1, that is the J plus 1 iterate, is P of J times exponential of minus mj by RT. Right? And then maybe stop. When do we stop? Because we also need to have a way to stop the algorithm. Right? Right? So we can stop the algorithm as maybe P of A plus 1 minus P of A is less than some epsilon. So if it doesn't change within a tolerance limit, then we say we have determined the saturation pressure to that accuracy. So we may then take either Pj plus 1 or Pj, whichever we want. So we can then take Pj to be equal to V1 sat, and then whatever volume I have found, right? So VL of J becomes VL and VB, and the procedure is complete. So it's a bit, calculating the cubic roots, very difficult for you to do it iteratively. Calculator, maybe you can calculate the roots of a cubic equation, but it's easier done using a MATLAB or some tool where you write a short program by which this iteration is done automatically, that you don't have to do it every time. Right? So it's easier done. So the procedure to calculate the saturation pressure is best done numerically on the computer rather than by hand. And it will really be very tiresome to, we don't know how fast this is going to converge, how many calculations, iterations you would have to make, right? But one step, you should know how to choose the initial pressure. You should know what to do with it, how to calculate the corresponding value, the volumes, and calculate this quantity M, and then you should know how to proceed to the next step. You should know where to stop or when to stop. This is any algorithm will have to have this initial guess, how you proceed with the initial guess, how you go to the next stage, and how you stop the iteration process. So you should be aware of all of these, right? And at least be able to carry out one iteration in the whole calculation. We'll look at some specific examples later on. Are there any questions on the calculation of saturation pressure? Yes? That's what, we're getting it from here. You can see whether if, what happens if M0 is greater than 0. If M0 is greater than 0, P of 1 would be less than P0, right? Can we say that? Right? If M0 is greater than, let us see whether that is what I want. That's exactly what I want. So the minus sign accomplishes what we want. What we want is to change the pressure. We want to increase, we've said, how geometrically we can easily see that if M0 is greater than 0, P of 1 is less than P0, must decrease. And then if M0 is less than 0, how the pressure should be increased, and this accomplishes that. That's why do you have the exponential minus m by RT? For that I have given a reasoning in terms of the Fugacity, justification in terms of the Fugacity. Right? So all I have done is taken this, which I picked up from the book, this, and I have translated it in terms of M0, which is what I recommend that you use for your calculation. Why there is a need. So if you look at the Fugacity formula, to have a big integral, right, RT by P minus P, and then you have some other terms. There is no need to calculate all those terms for first the liquid and then for the vapor. It's a very much more cumbersome process. Rather just calculate this, which I have got from that by subtracting the two. So when I have a simpler equation by subtracting the two, there is no need to go back again and calculate each quantity. What I have done is I have given you the subtracted final expression. So in what the book suggests, you calculate each expression separately at every iterate. Obviously that's very cumbersome and more time consuming. So numerically in a computer these calculations might take very little time. You have to do a lot of iterations. There's always a need to reduce the number of computations you have to do. Any other questions? So this is nothing but these two are entirely equivalent. If you can understand this, then you should be just express it into M. Yes? No, that's that's just one way. There's no unique way of obtaining the pressure. What we want to do is, if m naught greater than 0, V1 less than V0, this is our objective. You can do it in infinite number of ways probably. This is one way of doing it. Scale it in terms of the Fibonacci. There's no unique way to do it. You can also do it like this, plus delta P minus delta P. You can also do it. Maybe there's some other more efficient way of updating the pressure. I don't know, right? But this is one of the ways of doing it. And I'm giving you a rationale for why that is chosen. That's all. Anything else? So now what we can do is to get the other quantities associated with phase transition. The more other important, equally important. Scientific method is absolutely essential. So now I have gone. That's the first step. So from T1 is given, and I've got T1 sat, P1L, and P1B. Now the rest of the step is very straightforward. Suppose I want to calculate the enthalpy of vaporization. So again I look at the enthalpy of the departure function. What does the departure function say? Departure function says integral infinity to d1, right? d1 dt by dt. I use the same trick now everywhere. Whereas v1 minus r v1. This is what I have. So if I want the enthalpy of vaporization, all I will do is I type in Hp and subtract it from HL. These two are equal, so you get Hp minus HL again. This is the enthalpy of vaporization, the latent heat as it is called, so very important quantity associated with liquid vapor transition. So this can be easily written as V1M to V1B. Plus V1 sand. Again the RT1 factor will cancel out. So I calculate Hv minus Hit separately. Calculate Hi minus Hit, subtract the two, I get this. So given any equation of scale, I can also get the enthalpy of vaporization. There's also some books also talk about the entropy of vaporization. It can be easily shown. All of this depends on T1. The derivative will determine. Can be easily seen to be Hv minus Hi at T1 divided by T. Because if you look at the definition, S is actually G is H minus Ts. So S is actually H minus G by T. General definition. If you are looking at SV minus SL, you can clearly see that it would have HV minus HL, and then you get GV minus G which is 0, because of the equality of chemical potential means the equality of the gives free energy of the liquid and vapor. So that term will cancel, so you automatically get this. So I can get the entropy of vaporization. Gives free energy of vaporization is 0. Now I can also get the internal energy of vaporization. You can easily show that that is given by, it will just involve this integral. Because I haven't looked at the Helmholtz free energy of vaporization. Don't give much importance to it. That can be easily obtained. If I know E and S, EV minus EL and SV minus SL, you can easily get AB minus AL, because A is simply E minus TS. So AB minus AL would be EV minus EL minus P times SV minus SL, or rather T1 if you wanted at a particular temperature. So this would just be all this integral, just the integral. So that is this. Now, look at the significance of these equations. You look at this equation that gives you the saturation pressure. And look at all these quantities, because that saturation pressure basically contains, there's also a quantity of phase transition, which is a Gibbs free energy. That basically represents that. It's actually equal to the Gibbs free energy of transition. The transition means a change from one state to another. We've seen changes from one state to another within a phase. Right? That is the same phase. Now there are two possibilities. One, the temperature alone changes in this. Pressure alone changes, or both temperature and pressure could change. That's the most general case. Now this phase transition presents a unique case for a pure component where the temperature and pressure are fixed, but yet there is a change in properties. Right? So if you saw earlier changes of state, you get two terms, one which contains the derivative of the property with respect to pressure or volume, that is related to the equation of state. Another that will contain the specific heat. So you need basically two inputs to calculate any change of state, property change of state, right, within a single phase. But if there is only a change in pressure or volume and no change in temperature, then the equation of state alone will give you that change. Right? And if there is only a change in temperature, then the specific heat data alone at that pressure or volume would give you that change. But if there is a change of state within a phase from one state to another, let's say T1, T1, T2, you need where P1 is not equal to T2 and T1 is not equal to T2. This is now I'm talking about a single phase transition. That is transition within a phase from one state to another. So there is no change of phase. Right? So this requires this input, the equation of state plus CB or CB data. We have seen that. But now you come to this phase transition, right? The same, of course you would expect that nothing is then needed because for the phase transition both temperature and pressure are the same. However, that is not the case. There is still a change in property taking place. Now if you look at all these equations which determine changes taking place from one phase to another, which involves a phase transition, you will see that the only input is the equation of state. So many in the past have questioned how, for instance, you can get the energy change without any specific heat information, HV and HL. And also this also involves an energy change, namely the Gibbs free energy change. How you can get that without ever getting the specific heat and with just the equation of state, because the equation of state is not a fundamental equation. So how that alone can give you all the changes associated with phase transition, right? So that's the reason is because there's a fundamental flaw with this equation itself, which is not recognized widely. The flaw has to come because if you recall, whenever I looked at this is within a phase. No phase change, but state change. We were very careful to point out that whenever you're devising a path from that one point to another on the PT domain, you have to make sure that there is no phase change, then only those formulas are valid. Right? However, when I calculated this, UV there is no problem. So let's look at what we did with UV. Effectively what we are doing is we are now let us say I choose some P naught. Now this is a possible liquid state and this is a possible vapor state. So I am now calculating the chemical potential departure function corresponding to this chosen vapor state. So I am basically iterating from the ideal gas state to this. There is no problem. Departure function formula we said are valid as long as there is no change of phase. However, that important rule that I gave, that I violated when calculating the liquid chemical potential, because how do you calculate the liquid chemical potential? You are going from the ideal gas to the liquid state, and there is obviously a phase transition. But I am avoiding that, taking that into account by integrating effectively along this unstable part, going all the way around and here, and then coming back to the liquid state at the same pressure. So there is a change of state there, which I am avoiding by using the portion of the equation of state between the 2 points. That is fundamentally actually not correct. And if you were to do it correctly, this equation has to be corrected. But however, we go into the nature of the correction later, right? But for now, you have to remember that while all these, so now let us see what is the practical advantage of this. Because what we said was a departure function formula are useful within the gas phase. For any change of state within the gas phase, the moment you have a transition from the gas to the liquid phase in between two states, then you have to take the phase change into account, and we seem to have got some formula at least, even though these have to be corrected later on. But right now we have got some formula that calculates the phase change, and we have seen for that important is to calculate first the saturation pressure, and then you can calculate all these properties. It does have a fundamental flaw, all of these formula, but we will see how to correct it later. But let us now look at a particular change of state which involves phase change. We consider one such. So for that, what I will do is I consider first temperature T1. I'm just drawing the isotherm corresponding to that. Now I choose another higher temperature, let's say T2, and I will look at the isotherm. Now I am going to fix the two states, making sure that I necessarily have to encounter a change of phase. So P1 I will choose here. So let's say this is the saturation pressure, P1 sat, and this is the saturation pressure, P2 sat. Right? So now I have all the tools within me to calculate the saturation pressure and then all various properties associated with the change of phase. Even though with the caution I said that these have to be corrected later on. But let's proceed. This is a good zeroth order approximation, let's say. Right? One thing is that these formula will be valid the closer you go to the critical temperature. Because the whole phase, the whole of this is to look at properties of, this is the triple point, this is the critical point, right? And we are basically tracing not only this curve but various changes like enthalpy change and so on all along this curve. So clearly, since we have pointed out, right, that the difference between the vapor and liquid properties become closer and closer as we go towards the critical point, it will turn out that the Maxwell's rule is a good approximation for states close to the critical point. So at least you know, even though there is a fundamental flaw with these formula theoretically, that there will be a good approximation reasonably close to the critical. How close it is depends on substance to substance, right? But certainly it will have some validity at least, some range of value. So we can even say, even though there is a fundamental flaw with these equations, we will say that we are focusing on that part of the temperature range where these are reasonably good approximation, and then proceed to do some calculations based on these equations, right? So I fix the pressure P1 here, right? And then the P2 I will choose here, well above the saturation, both of the saturation pressures. So now what I want is to calculate any property. It could be enthalpy, internal energy, or anything. So I want to calculate this. So now you have to devise a path any infinite number of paths are available, but let me point out just two paths, much the same way we looked at two paths earlier, right? One could be, I reach, so now this portion you have to sort of forget, because I have calculated the saturation pressure, so I am concerned only with this, right? So one could be, you consider the path as being made from here to here, and then the transition, and then from P1 sat to, we could go along, continue to go along up to P2, and then reach the, so this could be one path. This would be one path that will take me from P1, T1 to P2, T2. Let us see what is involved in these paths. So I can write U, so I will call this, it is denoted by the pressure and temperature. So U of P2, T2 minus U of P1, T1. Would be U of P2, T2. This is why I have to calculate them. Again, I am choosing a constant temperature path and constant pressure paths to reach the state. But in between I also have to handle a path which actually involves no pressure or temperature, but I still have to account for that. That is why it's important to know this phase diagram. Otherwise I simply miss that. And it could be a significant addition to the overall property change. If you miss out for instance HV minus HO, it could be a significant addition. In fact, the latent heats are much more usually than the specific heats or the sensible heat. Right? So U of P2, T2. Now this is same pressure, but U of P2, T1 minus. That is one part. That is will give the change between these two states. That you can clearly see is entirely in the liquid phase. Now the other one, so I am now coming from P2 to P1 sat, right? But now at the same temperature, so that could be plus U of P2 P1 minus U of P1 sat P1. This is actually UL. Right? That is the liquid, saturated liquid corresponding to T1. I've reached that. Now this part is the one you are bound to forget if you don't look at it from this angle, because it's neither a change in temperature nor a change in pressure, right? It's like a point of singularity or discontinuity, but I have to take that into account. So I'll write this as UL minus UV, and then I have plus UV minus, so now I am entirely in the gas part of the isotherm. So that is UV minus U of P1 T1. First of all, I have indicated the path and I have calculated the difference between specific states, but you can clearly see the purely ultimate point U of P2 T2 minus U of P2 T1. That is cancelling. UL and UL is cancelling. UV and UV is cancelling, and I am getting this. Certainly without some kind of a path, you cannot just directly calculate these two differences, as you can see. Right? So now how do we calculate this? This is now in the this what expression will you write? This is T1 T2, because it involves only a temperature change, and this will be dU by dP. So I put a superscript liquid to indicate that this is in the liquid phase. That might be important because there are certain properties that don't change much within the liquid phase, and so they may be neglected. Yes, dou T. plus, again this is in the liquid phase, but this is now involving a change in pressure at a certain temperature T1. So that should now be dUL by dP T1 dE. Obviously the integral would be from P1 sat to P2. Now both of these are in the liquid phase, so the same equations that we used earlier would appear. So for instance, if this were H, so this would involve the specific heat at that pressure, liquid specific heat at that pressure. This would be entirely dependent on the equation of state, but it is integration done in the liquid side of the isotherm. So this I can get it, but for this I need specific heat data. For this I need, so it's important to remember that it is liquid, because for instance specific heats of liquid do not change that much with pressure. It's important, that's a physical fact that you have to be aware of. Certain properties of the liquid in general, it's a good rule of thumb that liquid properties do not change significantly with pressure. So that will be very useful if you have specific heat data at some pressure that nearby, that would be sufficient. You don't exactly have to have it at P2. So it's important to keep in mind the distinction in the properties of the liquid phase versus the gas phase, right? So then I have UL minus UV, for which I need to calculate the sat. P1 sat is what I need. I don't need P2 sat for this part. So I need to calculate first P1 sat, right? Because I can just give you that this is P1 T1 and P2 T2, not telling you anything about where they are. So you first you have to find out the relative positioning of P1 T1 and P2 T2 with respect to both P1 sat as well as P2 sat. Because I can use another thought where you need to know what P2 sat is. The first thing you have to determine that, right? So once you determine, then you know exactly where these the intermediate states are, and you can easily write down this path forward. So then this, the last term would be in the gas phase, and it is to see what this is. I write this as U of, right, P1 sat P1. That's what it is, but it is UV actually, right? But it is U P1 sat. But this whole path is entirely within the gas phase. There is no. It's important to know that that is UV, but it is at this point. So I am integrating from here to here. There is no discontinuity there, so I can directly use the derivative from P1 to P1 sat of dUg by dV P1. Interestingly, you will see this is the only term here for this part which is in the gas phase. So I don't really need even for this, because this can be directly obtained from the equation of state. I don't even need to know the departure function formula, right? So that is it. Another part which I will leave it as an exercise for you would be to go from at P1 to go to P2, right? This is another part. And then go all the way up to P2 sat, and then evaluate this transition at T2 between the liquid and vapor, and then reach P2 T2. So here you will see that you could probably find use for the departure to calculate this difference, which is entirely in the gas phase. Then I can integrate all along the same temperature, so I need only the equation of state. For this phase transition at T2, properties will have to come in. And then I am integrating along the liquid part of the isotherm at T2. So one which involves two segments in the liquid phase, one which involves only one segment. So there is a difference in the parts, but the final answer has to be the same. Are there any questions? So we will continue tomorrow.